Here's a problem on fluid pressure and force. We're going to add up all the fluid pressure on a side of a tank. So problem 19, a cylindrical oil storage tank of diameter 4 feet and length 8 feet is lying on its side. If the tank is half full of oil that weighs 50 pounds per cubic foot, find the force exerted by the oil on one end of the tank. So I have to draw a picture of one end of the tank. That's from page 564 in Tan's calculus text, by the way. Here's a picture. Diameter 4, the oil is half full. There's the end of my tank. The density is 50 pounds per cubic foot. Remember, the force exerted out on this side equals the density times the height at a point y. So if this were, say, a point y, I have to tell you this number here. This is the height at y. How deep is that liquid? That's going to tell you the force, the pressure per square unit, in this case per square foot, and then how much force is there at this depth? Well, you'd have to have a little rectangle here. What's the area of that rectangle? Well, it's the length of that rectangle. The length of that rectangle we refer to as L of y, times the height of that rectangle, which is dy from C, that's going to be the bottom of the tank, to D, which is here. Now we get a little decision here. There's a couple of different ways to do this because we don't have a coordinate system imposed. So do I want y to be down here, y equals 0 to be down here, y equals 0 to be up here, y equals 0 to be there? I typically, when I'm dealing with circles, put the origin at the middle. That makes the formula for the circle easier. So this is x squared plus y squared equals 2 squared, radius squared. That's going to make it easier to compute with these things. You can still do it here, but a circle centered not at the origin has a little bit more complicated formula. Okay, so in our case, the density is 50 pounds per cubic foot. Since I've got the origin here, this is going to be -2 at the bottom, up to 0 here. What's the height? Well, if I'm down, say, 1.5, y negative 1.5, the height of the liquid above that is 1.5, so a negative number gives me a positive. That's my height. What's the length? Well, somehow, when I'm down at a depth y, I'd like to know the x-coordinate, right? The x and y coordinates of this satisfy this equation. And now I double that x-coordinate there to get that whole length. So how do I get that x-coordinate here in terms of y? Well, x squared equals 4 minus y squared. That means x equals, if I wanted this value, I'd take the negative square root here, I take the positive square root of 4 minus y squared. So 2 root 4 minus y squared, okay, times dy. Well, this is just textbook setup for a u substitution. Let's think about that. If u equals 4 minus y squared, then du, this is just really nice and convenient, -2y dy. We'll notice that I have -2y dy just sitting there. Some days it goes your way. So I'm going to integrate this from y equals -2 to y equals 0 of, this is all my du, and so I just have the square root of u, or u to the 1/2 power. Now if you're integrating u to the 1/2 power, that of course is u to the 3/2 times the reciprocal of that, which is 2/3, evaluated from y equals -2. Right, I write my y in so I can remember I can't just plug these values in for u. I actually have to, let's see, 50 times 2, I guess I'll write this as 100/3, and then this is to the 3/2. That's 4 minus y squared to the 3/2, and I'm evaluating that at 0 and -2. So let's see what happens there. I have 100/3. If I plug in 0 here, I get 4. 4 to the 1/2 is 2, to the 3rd is 8. So I get 8. Then if I plug in I'm going to subtract that from what I get when I plug in -2. If I plug in -2, of course, squared, that's 4. 4 minus 4 is 0. Life is good, so I get 800 thirds. And notice if this is pounds per cubic foot, and I'm integrating something that is in terms of feet and feet and feet, I actually get out this poundage.